Let's try pink today. So I thought today's lecture we would just cover one bit of chapter 18 that we haven't talked about yet, which is one of the homework problems that people are having difficulty with. And then we'd push onward and upward into chapter 19 territory. So let's talk a little bit about electron drift. Okay, and this is related to your homework problem 1855. So the idea is the following. When we have a wire, right, our wire looks like this. It's got a cross-sectional area of A. It's got some length associated with it, L. And when current flows down the wire, current I, we know what that means, right? What that means is that little electrons in there are actually drifting to the left. They're actually bouncing around all over the place, but there is some net drift, V sub d, to the left, okay? And that's what's called the drift velocity. Okay, they actually bounce up and down a lot and move slowly to the left. As we're going to see, the drift velocity can be rather slow. So how do we calculate this drift velocity? Well, let's go back to the idea of delta Q, right? Delta Q is the amount of charge that's going to move. And if I think about what that really means is it's the number of charges n times the charge of each particle, Q. Okay, this is the number of charges, and that's the charge on each one. All right, but the number of charges we can write as something else. We can write the number of charges as a number density times a volume. And this n is the number density. It's the number per unit volume. And this is, of course, the volume of our sample. All right. Q is the charge on each one, and that is, of course, 1 electron. Okay, and we know what that is. That's 1.6 times 10 to the minus 19 coulombs, and it's got a negative sign on it. Okay. If that is the amount of charge, can we write it in terms of things that we know here, like the drift velocity? And let's redraw this picture and talk about that. Here is a portion of our wire. It has cross-sectional area A, and it has a length L. L is related to the drift velocity because if I think about an electron moving along at Vd, it's going to cover L in an amount of time, delta t. And so that distance L is just the drift velocity times delta t. All right. But if I do that, then I can calculate the volume of this cylinder. The volume is just the area times the length, and so the volume becomes A times Vd delta t. And now we can put that into this equation over here. we said the number of charges, N, is equal to number density times volume. And so it looks like it's just N times A times VD delta T. And now we can write all this in terms of the current. I, we said, was delta Q over delta T. And delta Q, we said, was N, little n, A, VD, delta T. And we're going to multiply by the charge of the electron. Don't worry if it's positive or negative. And then we're going to divide by delta T. And so look what happens. The delta T cancels out, and we get a nice little relationship. Current is equal to NA V sub D times E. Okay, this is the current in the wire. It depends on the number density. It depends on the cross-sectional area. It depends on the drift velocity, and it depends on the charge on that electron. Don't worry if this is positive or negative. We're just talking about magnitudes here. All right, with this information, can we attack problem 1855? So let's take a look at 1855. In my problem, it says the following. I have a wire that has a particular diameter D, and my number is D equals 0.65 millimeters. And it says it carries a current of 2.3 microamps. The molar mass of copper is 63.5 grams per mole. Okay, so there is some mass density, which is 63.5 grams per mole. And it's, I'm sorry, that's the molar mass, which I think they were using rho sub D for that. And then the mass density is 8,900 kilograms per cubic meter. And then finally, of course, they tell us Avogadro's number, which is 6.02 times 10 to the 23, and that is the particles in a mole. Okay. Do we have enough information to solve this thing for the drift velocity? Well, we have I, we have the current. We don't really have A yet, but they give us a diameter, so we can probably calculate A. We, of course, know the electron charge. We're solving for V sub D, the drift velocity. And what is not really clear yet is, can we get this number density N? All right, let's rewrite this equation, and we want to solve for drift velocity. So let's do that. V sub D is going to be I divided by little n times A times E. And now we have to worry about what these different things are. Okay, little n. Little n is going to be how many charges there are in a given volume. We know how many charges are in 1 mole, so if we can calculate the volume of 1 mole, then we'll have it. And the volume of 1 mole is going to be related to the mass density and the molar density. And so it's going to be 8,900 kilograms. And then we have to have 63.5 grams per mole. That's not really SI units, so let's convert this. 63.5 times 10 to the minus 3 kilograms per mole. Anything else not in SI units? Yeah, current, right? 2.3 times 10 to the minus 6 amps. D is also not. It's 0.65 times 10 to the minus 3 meters. And then everything else is good. Okay, so down in the bottom, we're going to need this 63.5 times 10 to the minus 3 kilograms per mole. That's going to go right there. And then dividing that, we're going to need the mass density, rho sub mass. And let's plug in some numbers here and let's see if the units work out right. Okay, so we've got 6.02 times 10 to the 23. And then rho d, we've got 63.5 times 10 to the minus 3 kilograms per mole. And we're going to divide by 8,900 kilograms per cubic meter. And it looks like the kilograms are going to cancel out, and we're going to end up with something per cubic meter. And so somebody punch those numbers into your calculator and tell me what we get, and it looks like the units are going to work out just fine. Okay, so that is our little number n. What about A? A is, of course, the cross-sectional area of the wire, which is pi r squared, which is pi times d over 2 quantity squared. And we know what d is. So this becomes pi times 0.65 times 10 to the minus 3. And we're going to divide that by 2. And we're going to square that whole thing. And if somebody gets a number for that one, let me know. Would anybody get a number for this one? 8.4. 8.4 times 10 to the 28. And the units are meters to the minus 3. Right? That's good because this is number density, so it should be number per volume. Okay. Can everybody see that okay on the right side of the board? Okay, let me know if I go off screen over there. And then what about this one right here? Anybody get a number for that, the area? Somebody else confirm that? Sounds about right. And then that's going to be square meters. Okay, and so now we should be able to put all of this stuff in for the drift velocity. So let's try that. Let's see, we don't need this stuff anymore. So we get drift velocity is current over NAE, which is 2.3 times 10 to the minus 6 divided by the number density, which is 8.4 times 10 to the 28. A, we said, was 3.3 times 10 to the minus 7. And E is, of course, 1.6 times 10 to the minus 19. So if somebody run those numbers in your calculator, I'll approximate it here. Let's see, we've got a 8 times 3, that's 8.4 times 3.3, that's got to be close to 30 times 1.5. That's got to be around 45, so we've got 2 over 45, 2.3 over 45, which is like 2 over 40. And then we've got 10 to the what? Down at the bottom, we've got 28. We're going to subtract 7, so we get 21. And then we're going to subtract 19, so we get a 10 to the 2. Is that right? And if we subtract 2 from that one, we should get 10 to the minus 8. So 2 over 40 is pretty close to 0.04 times 10 to the minus 8. So I'm going to say this is about 4 times 10 to the minus 10. Anybody get a real number?
5.2.
5? 5.2 times 10 to the minus 10. Okay, and that is SI units, meters per second. Okay, let's try it, see if we're right. It's a lot of numbers here. 5.2, and then we got to do our times 10 to the minus 10. And the units are meters per second. Should we click submit? Let's try it. Oh, we got the green box. Correct. All right. It's very exciting when you get that green box, isn't it? Okay, 5.2 times 10 to the minus 10 meters per second. If you're still having trouble with this one, go to the book and look at example 1814 because it does this problem nearly explicitly right there. So, is this a big number or a small number?
Small.
It says that that electron is going to drift at 5.2 times 10 to the minus 10 meters per second. That's barely moving at all, right? If I had to go 1 meter, it would take me like 10 to the 10 seconds to go 1 meter. So, does that mean when you turn on your light bulb that it's going to take forever for the light bulb to actually turn on because those electrons have to travel all the way from the switch up to the light bulb? No, that's not what happens, right? What happens? Why does your light bulb turn on right away when you turn that switch on? This is another one of your homework problems, by the way. So, a wire, of course, has atoms everywhere. So if I put an electron right there, there's going to be another electron right next to it, and another one right next to it, and another one right next to it. So that first electron that's going to move, all it has to do is bump into the next one. And if it bumps into the next one, then that one bumps into the next one, and that one bumps into the next one. And eventually, one of those is going to light up your light bulb. And that happens very quickly. Okay? Electric signals travel fast. Okay, they are pretty close to the speed of light, c. When you turn on the switch, that signal propagates down the wire at nearly the speed of light, even though every individual electron doesn't move very fast at all. Okay, really, really slowly. And so when you turn on the switch, that last electron by the filament that gets pushed hits the next one, all of those heat up in the filament, create light. So you don't have to send that electron all the way to the filament. It's going to take a long time to get to the filament. But the electrical signal is going to propagate very quickly. Okay, any questions about that one? You guys find that one challenging? Hopefully, that was supposed to be one of the more challenging ones on the homework. If you're totally bored, let me know and we'll get some harder homework problems. No problem. So we're going to push onward and upward, and we're going to talk about circuits in a little more detail. We've introduced the idea of the basic circuit with one battery and one resistor, but let's see if we can make them more complicated. So when we had a simple circuit, it looked like this: voltage and resistor. That led to a current I which flowed around the circuit, and we know what that current is because it's governed by Ohm's law. The goal of this chapter is to simplify circuits such that they look like this. Okay? If you can simplify complicated circuits to the point where they look like this, then you can understand everything about that circuit because Ohm's law applies just like that, V equals IR. So let's take the case where we have not just one resistor, but two resistors in series. So here's my battery. Here is resistor 1. Here is resistor 2. And now I want to get it to look back like this. Right? I want it to look like a simple circuit again. So how do I do that? Well, I just draw it again and label this thing something else. Now it looks like that. The only difference is it's called R sub S instead of R. How does R sub 1, R sub 2 relate to R sub S? Well, this is called a series circuit because I've added those resistors in series, one after the other. And when I do that, R sub S is just R1 plus R2. No problem. Ohm's law then applies. What's the current I? It is V equals I R sub S. And now you know everything about that circuit. What about when we do this? Let's add the resistors in parallel. There's my voltage V. Now I have R1 and R2 in parallel. How do I think about that? Well, the way I think about it is the following. There are, in fact, two current paths. When the current comes, it splits and goes two different ways around the circuit, and then it comes back together. Okay? So it's like my river splitting into two and going through two different paths. Okay? The end result of doing that is you don't just add up the resistors like we did before, you have to add currents. Okay. Here we were just adding resistors. But now what we're going to do is we're going to add currents, and we know that current goes like 1 over resistance, right? V equals IR, so current equals V over R. And when I do that, I can rewrite this as the following. We call it R sub P, resistors in parallel. And the rule for resistors in parallel is 1 over Rp equals 1 over R1 plus 1 over R2. This one is series. This one is parallel. The way you get to this is you add up the currents. We would have V over R equals V over R1 plus V over R2. Cancel out all the V's, and you get 1 over Rp equals 1 over R1 plus 1 over R2. Let's say we take a battery, V. We have resistor, R1. And then we're going to have two resistors in parallel. like so, R2 and R3. And the goal is to simplify this to just a battery and one resistor. Okay? So how do I do it? Well, I do it in 2 steps. Step number 1 is simplify the parallel. Okay? Let's simplify this portion right here. So if I do that, I can rewrite this as the following. R1 is still there. We haven't changed it. Whoops. But this one becomes R parallel. Okay? And we know what R parallel is because 1 over R parallel equals 1 over R1 plus 1 over R2. And if you want to write what R parallel is, you can do that. 1 over RP equals, what do I do with this stuff? I multiply by R2 up there, I multiply by R1 up there, and then I put a common denominator. And then I can flip the right and the left. And so we get RP is equal to R1, R2 divided by R2 plus R1. That's what RP is. Step 2 is now we get rid of the series. And we know how to do that. RS, where RS is equal to R1 plus RP. And look, we now know what RP is. So RS is equal to R1 plus R1, R2 divided by R2 plus R1. And in fact, I can pull out a common factor here of R1, and I get R1 times 1 plus R2 over R2 plus R1. And you could simplify it further if you want, but that's fine. So one of the questions now is, what's the current going through this circuit? What is this current I?
Wouldn't the initial R1 over there be R3 in the first parallel set?
Right here?
In the first parallel set.
Yeah. You're totally right. Thank you. These were R2 and R3. Good. So change all the R1s in there to R3s. Perfect. And now let's be a little bit more careful over here. Samuel, we can edit out that part, right? R1 plus RP, which is R2, R3, divided by R2 plus R3. Good, thank you. That makes a little more sense. Okay, so we've simplified the circuit to that. One battery, one resistor, and it has a value of R sub S. And if you're calculating what the resistance is, R sub S, you just punch in some numbers there. If you want to calculate the current now, you can go back to Ohm's law. If you have a simple circuit, then Ohm's law applies. And so I is just going to be V divided by R sub S, where this thing is your R sub S. Okay, let's try another example. Let's try this example right here. Okay, so let's let our circuit look like that. And now let's label these things R1, R2, R3, and R4. And let's see if we can simplify this to our simple circuit. So the first step is to start in the innards and then work your way out. So the innards here are going to be R1 and R2 next to each other. So the first step is going to be get rid of those. We change that to an RS. This is still R3. And then we still have R4 down below. RS is simply just R1 plus R2. Okay, this is supposed to be a 3. And now we're almost back to where we were just a second ago. The next step is this. This is RP, that is R4. RP is 1 over RP equals 1 over RS plus 1 over R3. And then the final step is that, and we'll call that one R sub S2, how about, since we already used R sub S. And R sub S2 is just going to be RP plus R4. Okay, so if you know all the resistances, you can calculate RS. If you calculate RS, you can then calculate RP. If you calculate RP, you can calculate the final resistance RS2. And then Ohm's law applies. V equals I times RS2. And so you can calculate the total current in that circuit. Obviously, you can do this for any number of resistors you want in any combination you want. Just remember, you should always start at the innermost connections where it's deepest in the circuit and then work your way out to simplify. Okay, questions about that?
No question.
Yeah.
Where do we see such complicated circuits?
Pretty much every circuit you're going to come across will have stuff like this in it. Okay? And the reason that you might have complicated circuits like that is because you want to be able to supply different voltages to different devices. So there might be something that's attached here that needs a different voltage than the thing that's attached here or the thing that's attached there. Okay, so you can do all sorts of complicated voltage divisions as you go when you're building up circuits. Okay, let's talk about internal resistance. And this is what is the resistance inside of a battery. So a battery, the way we've drawn it, the ideal battery just looks like this. Okay, it is a voltage supply, V. There is positive on one side, negative on the other. But that's not really what's in a battery. A real battery has some internal resistance to it. So a real battery should really be modeled as this. A voltage plus an internal resistance. And that's this little lowercase r. Okay? What is the resistance inside a battery? So, if you have an ideal voltage supply, then that internal resistance is 0. Okay? And what it means is no matter what you connect to the battery, it's always going to be the same volts. Your 12-volt car battery, if you attach loads to it, it's still going to be 12 volts. But in reality, R is never 0. And for a car battery, R is approximately 0.01 ohms. Okay, it's something pretty small, but it is still real. Now, V of the battery is what's coming out here. Okay, what's coming out of the circuit, out of this circular region, is what you actually measure coming out of the battery. It's not only a voltage supply, it's a little internal resistance. Okay, and we call that the terminal voltage. So, we know what that is because we know what Ohm's law says. The battery terminal voltage is going to be the following. It's this ideal V minus the voltage drop across the resistor, and Ohm's law tells us that it is I times R. So if you're not drawing any current out of your battery, then the voltage is 12 volts. But as you start to draw more and more current out of the battery, the voltage drops a little bit. So let's see what it drops to when we are starting the car battery. When we're starting the engine using the battery as a current supply. Okay, so what we said in class was during start, that thing can be drawing 300 amps. So what is the voltage on those terminals? V on the terminals is going to be V minus IR, which is 12 volts minus I, 300 amps, times little r, which we said was 0.01 ohms. And so we get 12 volts minus, let's see, 300 times 0.01 is 3, right? That's 100th. Amp times ohms is also volts, and so you get 9 volts. Okay, and you can measure this. You guys have a little voltmeter, probably at home. You have one that you're playing with in the lab. If you connect this to your car battery and you look at the voltage on your car battery, it's going to read around 12 volts. Okay? But when you start the car, that voltage is going to lower to about 9 volts. After the car starts and this current goes back to 0, then it'll go back up to 12 volts. Okay? It's kind of a fun little experiment to do. All right, welcome back, everybody. Let's get you jump-started on your Chapter 19 homework, and let's look at one of them explicitly. This is number 1916, and it has a circuit there, and we need to figure out the equivalent resistance of the circuit. Okay, so let's draw the picture up here. So this circuit looks like the following. It's got a battery right there. I'll give you my values. It's 12 volts. And then there is a wire here. There is a resistor going up. There is another resistor going up. And then there is a wire going across. And there is a resistor right there. Okay, and this one is, we'll call it R1, R2, and R3. So the voltage supply was 12 volts. R1 in my numbers are, let's see, it's 820 ohms for that one. R2 is 680 ohms. And R3 is 960 ohms. Okay, we need to figure out the equivalent resistance of the circuit. Now, they draw it on the side just to play with your mind a little bit because we've always been drawing the batteries vertically. But we can just rotate this thing, right? So let's do that. Start with, we'll make the battery there. The wire goes up, and now it's going to go to two things. It's going to go to R1, and it's also going to go to R2. Okay. After you go through those resistors, the other side is connected to R3. And then it comes back to the battery. So this circuit is exactly the same as that circuit. All we did was rotate it to the right, and we moved some of the wires around, but we didn't change any of the important connections. All right, we know how to model this now. We just did this a second ago. First step is let's get rid of this parallel. So we rewrite the parallel resistors as Rp. We still have R3 hanging down there. And we know what Rp is. 1 over Rp equals 1 over R1 plus 1 over R2. And now at this point you could calculate Rp, right? Austin was asking about writing this in terms of common denominators. You could also just plug in those numbers and calculate Rp. So why don't we do that? 1 over Rp equals 1 over R1, which is 820 ohms, plus 1 over R2, which is 680 ohms. And why don't you guys plug those into your calculator and tell me what you get, and then take 1 over that number. Okay, after you take 1 over 820, you add 1 over 680, set equals, and then invert it, and that's Rp. And tell me what you get. 372 ohms. Somebody else concur on that one? Okay, good. So that's Rp. Now, we need to add those two in series. So we end up with this. Where Rs is now Rp plus R3. So it's 372 plus 960, which is 1332. And that is, of course, ohms. All right. The first question was determine the equivalent resistance of the circuit. That's this. Once you get down to the simple circuit, whatever that resistor is that's left, that is the equivalent resistance. Should we plug it in and try it? 1332, and the units are ohms. We got to go to the symbol guy. There it is. And we submit it. And it says correct. 1332 ohms. All right, so that was the first part. The second part says determine the voltage across the 820 ohm resistor. So they want the voltage across here. We'll call that V1. What is the voltage across resistor number 1? Aha! How do we do that? I think to do that, we're going to need a little bit more information. Okay, let's talk about Kirchoff's rules. Kirchoff's rules are the following. The first is called the junction rule, which says at a junction, the current in has to equal the current out. Okay, what does that mean? That means if I have a wire and it suddenly splits into two wires, whatever current is coming in here, let's say it's 10 amps, it has to go somewhere out of the junction. So it could be 5 amps going that way and 5 amps going that way, or it could be 7 amps going that way and 3 amps going the other way. Whatever current is coming into the junction has to go out of the junction. Namely, charge doesn't build up there, charge isn't depleted from there. There's no net buildup of charge, and so any charge coming in has to go out, which means the currents have to match up. How does that work when we're dealing with a circuit? Well, let's go back to our parallel circuit for a second. Let's say we have a battery, and now we're going to split into two different paths, R1 and R2. This thing right here is a junction. A junction is anywhere the wire splits into two or more wires. So that's a junction right there. And at that junction, we have to have current in equals current out. Okay? Current in is going to be I. Current out is whatever goes in that one plus whatever goes in that one. So we'll call it I going in, I1 to the left, I2 to the right. So I equals I1 plus I2. But we know what I is. I is the same as voltage over equivalent resistance of the whole thing, which is R parallel. Because that circuit we can draw like this. I1 is whatever voltage is across R1 divided by R1. But it's the same voltage, right? This is a wire all the way to the top of R1. And so that wire is an equipotential, and so the voltage across R1 is the battery voltage. But likewise, the voltage across R2 is also just the battery voltage. Okay? And so this is what we were talking about earlier. We can cross out all the V's, they're all the same, and we get the parallel series, or the parallel resistor rule, which says 1 over Rp equals 1 over R1 plus 1 over R2. Okay, this is a direct result of Kirchoff's junction rule. Okay, the second rule is called the loop rule. And the loop rule says the following. Around a circuit loop, the voltages that are rising minus the voltages that are dropping has to equal 0. So these would be like your batteries. These would be your resistors. Okay, so any circuit what it says is the voltage drops that you rise on minus the ones that you drop on have to be 0. So let's start right here. And let's go around the circuit like this. The very first thing I do is I go through a battery. And so I rise. I get plus V. The next thing is I go through a resistor. And so that is a drop of IR. And that's it for this simple circuit. And so I get back to 0 where I started from. And this is, of course, just Ohm's law, right? If I move IR over to the other side, I get that. And we say we're happy. But let's say that we have more than one resistor in there. Okay, let's see how this loop rule works. So let's do a simple battery again, but we're going to add two resistors. R1 and R2. And there's some current I that's flowing in this circuit. So once again, let's start right there, and we'll go around the circuit in that direction. So the first thing we do is we hit the battery. That's positive. We've gone from the negative terminal up in voltage to the positive terminal, so we have a plus V. And then we go through resistor R1. That's a voltage drop of IR1. And then we go through R2, and so that's a voltage drop of IR2. And all of that is equal to 0. And so we get back to what we already knew. If I put both those on the other side, I get IR1 plus IR2, or I times R1 plus R2, or I times R series. Now, in the problem that we were just looking at, they wanted to know the voltage across the 960 ohm resistor. So let's think about this for a second. Let's say that this is up here. We will call this VA. We will call this VB, and we will call this VC. And we'll draw everything relative to ground here. What can we say about VA? VA is just equal to the battery voltage V. But VB, the voltage here, is going to be less than that, right? VB is going to be the battery voltage V minus how much it drops through R1. Okay, so that's going to be a little bit less because you have current and you have resistance. VC is, of course, going to be 0, right? You're already down here. Okay, so let's see if we can do our problem and attack part B. Okay, so let's redraw the circuit the way we had it. We had voltage V, and then we had two in parallel, like so. And I think these were R1, R2, and R3. Is that how we had it, guys? Okay. And they want to know the voltage across the 820 ohm resistor, which is R2. So they want to know this voltage from there to there. And we'll call that V2. Okay, what is that voltage? Well, that's going to be the same as this. R3, this is RP, and they want to know the voltage across that, which is V2 or V1, or we could just call it VP. Okay, but I know the voltage drop across a resistor. The voltage drop across a resistor is just I times RP. That's what Kirchoff's rules or Ohm's law tells us. The voltage drop across a resistor is just that. So Do I know the current? Not quite yet, but we can get it very easily. This circuit becomes this circuit, where RS is equal to RP plus R3. And we said we knew that one, right? That was part A, which was, let's scroll back up. For our numbers, it was 1332 ohms. And so now you know what I is, because V equals I R sub S. So I equals V over R sub S. And so look, I can plug that in right here, and I get V over R sub S, all of that times RP. And now we have all those numbers, we can plug it in. So we have 12 volts. R sub S we said was 1332. R sub P we said was what? Was it 338 or something? You guys remember?
372.
Was it?
372.
372. Good, thank you. 372. And so now you just got to multiply this out. So somebody multiply that out and tell me what you get.
$3.4.
3.4. Is that right? 3.4 volts. Anybody else concur on that one? Sounds like a good number. Should we try it? 3.4 volts. Good. Got that one right. The last question is, well, part C is determine the voltage across the 960 ohm resistor, which is this one right here. Okay. And at this point, you probably don't really need to do any calculation, or at least not much of a calculation. Anybody be able to tell me what V3 is? I'll give you a hint. V, we said, was 12 volts. VP we just solved for. It was 3.4 volts. Yeah, so this has to be 12 minus 3.4, which is what? 8.6, hopefully. Add a 0.4, we get 9. Add 3, we get 12. And it better be 8.6 volts. Let's try it. 8.6. Very good. And then the last part was determine the voltage across the 680 ohm resistor. That's this resistor right here. We've already done that. That has to be the exact same as this voltage right here, because those are metal wires going all the way across. So the last part is also going to be 3.4 volts. Perfect.